Okay, so next we have my co-chair Shuai Li, who will be presenting on characterizing potential landing sites for future exploration of lunar surface water ice. Go ahead.
Okay, thank you, Ariel. So as we know, the surface exposed water ice was recently found in some lunar PSRs. Here's the map on your right side, North Pole and South Pole. We know it is important for in situ resource utilization, and also those ice may still preserve the features of their origins that may help to reveal the origins of water on the moon and the Earth, and even the inner solar system. However, PSRs reaching in water ice exposures are still lack of some detailed information for future exploration, particularly the ice content at each PSR and also the associated mineralogy. We still need further studies. And also, most important, how to estimate the water ice in the ice regolith mixtures has not been well studied, particularly when the ice abundance is low. That's the focus of this work. And also it is important for estimating ice for future mission data, such as Viper and Trailblazer will be launched soon. And the PSR is hosting abundant surface ices are potential landing sites for future exploration. And the data and keep the moon mineralogy mapper data used in this study at each PSR can be averaged to reduce the noise level. And then we can use the data to estimate the ice content and the mineralogy information. Here's one example at the Shoemaker PSR as shown here. The black curve is the average spectra of the whole PSR. You can see the prominent feature near 1 micron absorption, and also lack of a 2 micron absorption. And also we can average the M-cube pixel showing ice features as shown in the blue line. You can see the ice absorptions near 1.5 and 2 micron. The red curve is the average spectra near the crater rim. It's relatively featureless. Anyway, we can use this spectra to tell their ice content and mineral information. And the question is like which kind of which features or what features we should use to estimate ice content from the orbital data we have now. So here's a plot. I'm showing the spectra of pure ice as a blue line in comparison to the spectra of 2 Apollo samples, Apollo 11 sample and Apollo 16 sample. It shows very diagnostic absorption features in comparison to the typical lunar surface regolith. I'm going to introduce from the left, from the right to left, try to tell which will be the best to we can use to quantify the surface water ice. The first one is the molecular water bending absorption near 6 micron. It is very sensitive. This is fundamental. So this is very sensitive to the presence of molecular water. And the 4.5 micron absorption is the combination of molecular water bending and also the lattice vibration. They're also very strong. The strongest is near the 3 micron. Is due to the fundamental stretching of OH and all the presence of molecular water overtones. So because this absorption can be caused by both hydroxyl and molecular water, so it is very difficult and challenging to identify or discriminate whether molecular water present if you just solely use the 3 micron bands. And another one is also very strong. That's near 2 micron. This is due to the combination of OH stretching and the molecular water bending. So if you see a 2 micron feature like this, it can tell you the presence of molecular water. So that's the focus of the study. We're going to use the 2 micron feature. And again, the 1.5 micron can also be caused by both hydroxyl or molecular water. So it's it's not unique to identify molecular water. And the reflectance in the mid-IR feature is relatively low in comparison to visible. So maybe the emission feature will be emission spectra will be more useful than reflectance. Again, the focus of this work will be estimating ice content from the 2-micron absorption, and we use 2 different ways to quantify the ice content. First, we use the radiative transfer modeling to mix the ice and the regolith intermittently, and we use Hacking model and assume the particle size at the mean particle size measured from Apollo samples. And in this plot, I'm showing the inner members. This is the blue line is the pure ice, and the dark red line is Apollo 16 sample, and also a lunar analog sample, more glass, and also Apollo 11 sample. Here on the top right, I'm showing one example of adding more ice to the Apollo soils. You can see the change of the 2-micron absorption features stronger and stronger. And we can correlate with the band depth at a 2-micron with the ice content as shown in the bottom plot. You can see no matter which sample we use, the trend is very tight between the ice content and the band depth at a 2-micron, strong indicating we can use the 2-micron feature to identify water ice. And the second way, we did experiments in lab to mix real water ice with the lunar analog, the Morbid glass. So the Morbid glass spectra is shown in the left plot, and this in the middle plot, I'm showing the lab prepared water ice. You can see the absorption feature changes as you change the particle size. So that's why the particle size is important. Again, we assume the mean particle size as 70 micron as the mean particle size measured from Apollo samples. On the top right figure, I'm showing how the spectrum looks like when mixing ice and the basalt sample. And at the bottom right, I'm showing the correlation between the ice content and the band depth at a 2-micron. Again, you can see the trend is very tight. So put together, we can develop an empirical model for estimating water ice content from 2-micron absorption. As shown in the left figure, you can see both experiments and simulations, they follow on the same trend. And then we can derive this empirical correlation between ice content and the band depth. And this is very useful to determine the detection limit of water ice based on the 2-micron absorption with the given SNR as shown in the red plot. So for like a 1% detection limit, you may need like around 100 SNR, signal to noise ratio. And also it could be very useful for interpreting 2-micron absorption features of future mission data, for example, vapor trailblazer, because they all have measurements at this wavelength range. And then we can use the model to estimate the ice content at a Shoemaker PSR. This is the average spectrum, M-cube spectrum of all ice-bearing pixels. And we can have 2 different scenarios. Conservative scenario, we can assume like, you know, the part of the absorption is due to the noise, and we can roughly estimate the band depth. And also realistic scenario, we use the mean value to estimate band depth. So it gives you like around in the red dash box, give you around a 5% to like a 40% ice. And also we can tell the mineralogy from the average M-cube data. Again, this is a scatter light, so we cannot tell exactly the true continuum and also absorption shape, but a major feature should be there. And we compared it with the spectra of glasses found in Apollo samples, like agglutinates and Apollo orange glass. You can see they show a broad 1-micron absorption feature and a lack of 2-micron feature, suggesting dominantly glass. And future high-quality data may help to validate the M-cube observations. So in summary, a model is developed to derive water content from the 2-micron absorption features. Now the model can be used to assess the detection limit of water ice with the given SNR, and important for interpreting data for future missions. And the particle size regulates composition, maturity, and beam geometry we considered in future studies. The Shoemaker PSR we get is like at least a few % of water ice, and it regulates the dominant glasses. And we will perform data studies for remaining APSRs for future exploration of lunar surface ice. Okay, thank you.